When calculating definite integrals, we may encounter two different types of problems. The first one may happen if the limit of the integral has infinity or plus or minus infinity. This type of problem is called, in such a case, we call this problem an improper integral of type 1, which was the topic of another video. In this video, we will see improper integrals of type 2, where the problem is due to the integrand having a vertical asymptote in between or at the boundaries of the integral. So, in such a case, we will proceed similarly, just like for the improper integrals of type 1, we will approach those points where we may have a problem with limit. So, let's illustrate this with examples. Our first example is the integral of ln of x dx from 0 to 1. So, here the problem is at 0 because ln of x is not defined at 0. Let's see it geometrically. So, if we sketch the graph of ln of x, it may look like this: x, y. Here we have 0. We know ln of 1 is 0, so that the curve goes through 1. And the integral, the definite integral from 0 to 1 of ln of x means or gives us this area over here. As you can see, the area is not finite because the curve goes to infinity as x goes to 0. However, the value of the integral may be finite. If the value of the integral is finite, we will say this integral, this improper integral, converges and has a finite value. If not, if we have an infinite value, then we will say the improper integral diverges. So let's see what is the case over here. We will proceed with a limit. So I'm trying to integrate between 0 and 1, but at 0 I have a vertical asymptote. So that means I'm going to pick another value over here, let's say a, and I'm going to integrate between a and 1, and then let a go to 0 from the right hand side with the limit. So let's see. This is the same as limit as a goes to 0 from the right hand side of the integral of ln x dx from a to 1. As you can see, as a goes to 0 from the right, this is the same as from 0 to 1, the integral of ln of x from 0 to 1. So now, this is just a regular integral. Let's calculate this. You can calculate the integral of ln x by using integration by parts, which is another topic, but we already know that the integral of ln of x is x times ln of x minus x. And the limits, the upper limit is 1, the lower limit is a. Now let's put the limits. Limit as a goes to 0 from the right. So first the upper limit, if we plug in 1 for x, we have 1 times ln 1, which is 0. 0 times 1 is 0. So I have 0 minus 1. Then going to the lower limit, I have the minus sign in front, then a times ln of a, minus minus makes plus a. Okay? Because limit is a linear operator, so I can distribute it over the sum or difference, so I have minus 1 and then minus limit as a goes to 0 from the right hand side, a times ln a. Then I have limit as a goes to 0 of a, which is 0, so I don't need to write it. And let's see what we have here. Here we have 0 times ln of 0, which is, as you can see from here, my negative infinity. So this is kind of 0 times negative infinity, which is an indeterminate form. So in such a case, we can use L'Hopital's rule if we can turn this indeterminate form into another indeterminate form that we can apply the L'Hopital's rule, either 0 over 0 or infinity over infinity. So let's do this. This is minus 1 minus limit as a goes to 0 from the right, ln a over 1 over a, because 1 over a is the same as a. But now we have negative infinity over, as a goes to 0, from the right 1 over a goes to infinity. So in this case we have infinity over infinity. That means I can apply L'Hopital's rule over here, minus 1 minus limit as a goes to 0 from the right, using L'Hopital's rule. The derivative of ln a is 1 over a. Derivative of 1 over a is minus 1 over a squared. And this gives us minus 1 minus, as limit goes to 0 from the right hand side, I have 1 over a minus 1 over a squared. That makes us plus a over here, and this is minus 1 plus 0 gives me minus 1. So since this is a finite value, the area under the curve is minus 1. We say this improper integral is convergent. Our second example is the integral of tangent of x from 0 to pi over 2. This is again an improper integral of type 2 due to this pi over 2 over here, because we know that tangent pi over 2 is not defined and actually goes to infinity. Let's see this. If we want to sketch tangent of x, the function tangent, the tangent function has vertical asymptotes here at pi over 2, and there's a 0 over here. So the integral, the definite integral we are calculating gives us actually the area under the curve from 0 to pi over 2. And as you can see, we have a vertical asymptote over here. So again, I need to approach this limit, this point with limit. So instead of integrating from 0 to pi over 2, I'm going to integrate from 0 to some point b, and then let b approach pi over 2 from the left. So this integral can be written as limit b goes to pi over 2 from the left of integral of tangent of x, and tangent of x is the same as sine over x, sine of x over cosine of x. And actually the problem, the vertical asymptote, is due to cosine, which is not defined at, which is 0 at pi over 2, from 0 to b. Okay. Now let's calculate the integral by keeping the limit over here as b goes to pi over 2 from the left. Integral of tangent of x, this can be done by substitution. You can say, you can substitute u for cosine and do the substitution, which will give you minus ln of cosine of x. Why? Let's see, because ln, the derivative of ln cosine x is 1 over cosine times the derivative of the inside, which is minus sine. The minus sign cancels, so you have sine over cosine, which is tangent. And the limit, the upper limit is b, and the lower bound is 0. Okay, let's put them in. We have limit as b goes to pi over 2 from the left minus ln cosine b. Then for the lower bound, you have minus minus plus. And then if you plug in 0, cosine 0 is 1. And then you have ln 1, which is also 0. And let's check out this limit. As b goes to pi over 2, cosine pi over 2 goes to 0. And then ln 0 goes to negative infinity. Remember ln's graph. That was ln x. as x goes to 0, ln x goes to negative infinity. And with this minus over here, I have negative, negative, so plus infinity. So altogether, this gives me infinity. That means the area is not finite, or in other words, this improper integral is divergent. As our next example, consider this integral over here. Here we have an integral from a definite integral from 0 to 2, and if you check 0 or 2, the integrand doesn't have any asymptotes or any problem, any discontinuities, nothing at all. However, the problem occurs at 1, which is in this interval 0, 2, because 1 over 1 minus x squared is not defined at x equals 1. In fact, it has a vertical asymptote. Let's see this graphically. If we wanna, let's sketch this function x, y. We know we have a vertical asymptote at x equals 1. And then let's say this is 0. And we want to integrate from 0 to 2. This function looks like this. So the area we want to calculate is this one here, from 0, the area under the curve between 0 and 2. As you can see, the area is infinite. Let's see whether this improper integral of type 2 will converge or diverge. This is different than the previous two questions, two examples. Here, I want to calculate the integral between 0 and 2. However, the problem is at 1. So to overcome this issue, I'm going to pick up another point A, let's say A over here, and then integrate from 0 to A, and then let A go to 1. And similarly, here I will integrate from B to 2, and then let B go to 1 here in the limit form. And I can do this because integration is linear, so the integral from 0 to 2 is actually the integral from 0 to 1 plus from 1 to 2. So let's rewrite this as limit as A goes to 1 from the left, the integral from 0 to A, 1 over 1 minus x squared dx, plus limit as b goes to 1 from the right hand side, the integral from b to 2, 1 over 1 minus x parentheses squared dx. Okay. Now let's calculate these these integrals. The integral of 1 over 1 minus x squared is 1 over 1 minus x using the power rule. So I have 1 over 1 minus x from 0 to a, plus similarly here we have limit as b goes to 1 from the right hand side of 1 over 1 minus x with the limits 2 and b. Actually, it's enough to just calculate one of those and see whether it diverges. If it diverges, then the total must be divergent. However, in this case, I'm going to calculate both of them. So here I have limit as a goes to 1 from the left-hand side. Plugging the upper limit, I have 1 over 1 minus a minus, then putting the other one, here I have 1, plus limit as b goes to 1 from the right hand side. Using the upper limit, I have 1 over 1 minus 2, which is minus 1, minus, and using b in here, 1 over 1 minus b. Okay. let's check this limits. Here I have, as a goes to 1 from the left hand side, 1 minus 1 goes to 0, 1 over goes to infinity, because I'm approaching from the left. So this is actually infinity over here. Then here I have infinity, then minus 1, then minus 1 from here. And this, let's check this limit. As b goes to 1 from the right hand side, 1 minus 1 goes to 0, and then 1 over 0 goes to negative infinity because I'm approaching from the right. So with the minus sign in front, again I have plus infinity. So this gives me infinity minus 2, again infinity. So because the value is not finite, we say this improper integral is divergent. In this kind of questions, we need to be careful, because if you don't realize that this is an improper integral and calculate this as if it were a regular definite integral, let's see what happens. So if you think this is just a definite integral and you do this calculation, so that means you do the integral without partitioning the integral and taking the limits. So you will obtain 1 over 1 minus x with the limits 0, 2. And if you plug in those values, if you plug in 2, you will have minus 1, then minus, if you put 0, you will have minus 1, minus 2, which is finite. However, this is a wrong result. As a final example, let's consider the so-called q integral. This integral of 1 over x to the q from 0 to 1. As you can see, this is obviously an improper integral due to the 0 over here, because 1 over x is not defined at 0 and has a vertical asymptote. However, the value of this, or the behavior of this integral, depends on q, on the values of q. Let's see why. It's basically due to the power rule of the integration. So if q is 1, then this is 1 over x, whose integral is ln of x. And we know that ln 0 goes to negative infinity. That means if q is 1, then the integral is divergent. So let's consider the other cases. What happens if q is less than 1? If q is less than 1, let's say negative 1, negative 2, negative 3, so on, then this is 1 over x to a negative power, which in turn will give us, so for example, x squared, x cubed, and so on. Using the power rule, you will have for x squared, x cubed over 3, and with then plugging the boundaries, you won't have any problem at all. You will have a finite value. In this case, we say the improper integral is convergent for values of q less than 1. And finally, if q is greater than 1, let's see, for example, 2, then I have 1 over x squared, whose integral is minus 1 over x. In all those cases where q is greater than 1, antiderivative is 1 over x to some power, and when plugging the 0, you will have an infinity. That means the integral will diverge if q is greater than 1. So, and you can also use this q integral when applying comparison tests for improper integrals, which is a topic of another video. Today, we have seen improper integrals of type 2, where the problem is due to the vertical asymptote of the integrand. So in such integrals, we approach the points where we have a problem or where we have a vertical asymptote with limit, and then check the value of the outcome. So if we have a finite value, or if we have several integrals, if all of them are finite, then we say the integral, the improper integral, converges. and has a finite value. Otherwise, if one of the values of the integrals is infinite, then we say the improper integral diverges.